So this is another video in our sensitivity analysis series of videos. And in this video, I'm going to talk about relaxation and restriction of a linear programming model. So we start with relaxation. What is relaxation? Well, we will define relaxation as a kind of expansion of the feasible region by making constraints less restrictive. So for example, if I remove a constraint from the model, I am going to have a relaxation because this constraint perhaps was removing some, restricting the feasible region by removing some feasible points, and now I don't have this constraint. I may have more feasible points I can choose the optimal solution from. If I increase the right-hand side of a less than or equal constraint, right? Let's say I had 200 pumps and I said the used pumps less than or equal 200, now I increase it, right? That is like an increase of available resource. This will be a relaxation. And if I decrease the right-hand side of a greater or equal constraint, like let's say I have a minimum requirement for something, right? x1 plus x2 must be at least 100, and then I decrease this 100 to 50. That's also a relaxation, right? So generally, when we relax a binding constraint, then we should expect the optimal objective value to improve, or sometimes it might stay the same, in rare cases actually, right? But typically when you relax a binding constraint, let's say you had 200 pumps, but you increase the right-hand side of this constraint, the optimal objective function value will improve, right? So if this profit maximization improvement means it will increase. And when you relax a non-binding constraint, like we had an example in Aquaspa Hydrolux or hot tubs problem, there was one constraint, the feet of tubing, that was non-binding. Then if you relax it, it's not going to help the solution, the solver to find a better optimal solution. So the optimal objective function value will not improve, it will stay the same, and actually the solution will also stay the same, right? So let's consider some examples to see what we can say. And in fact, what I want to show you here is that right before we were looking at sensitivity analysis, but even if we don't have sensitivity analysis information, we can still conclude quite a lot just knowing what the optimal solution is and what the constraint that we're changing is and how it is changing. So here is the first question. An optimal solution of a certain model is x1, x2 is 10, 20, right? Optimal values. Then the model contains a constraint x1 plus 3x2 less than or equal 100. What if we increase the right-hand side of this constraint by 20, so we make this 120? Or what if we remove this constraint, right? So the first thing to see here is, was this a binding constraint? If it was binding, it must have been, the slack must have been 0, right? Can we calculate the slack? Well, we can see what was the left-hand side of this constraint, right? We can say left-hand side of this constraint, which is, right, x1, well, I can plug in the, right, star, plus 3x2 star, right? So if I take the left-hand side of this constraint, right, and I plug in the optimal solution, right, it will be, right, this is going to be 10 plus 3 times 20, right, that will be equal to 10 plus 60, so 70, right? So now if you take this and say, well, right-hand side minus left-hand side, which is slack, the absolute value of that left-hand side is 100, right? 100 minus 70, that is equal to 30, right? So this is not 0, right? Or more than 0, right? If the slack is not 0, that means, so this constraint was not binding, right? So what we said is if we relax a non-binding constraint, and these are both relaxations, if we increase the right-hand side of this constraint, which is like saying, well, there is 100 units of resource, what we allow now using even more, 120, right? And removing the constraint is even more, relaxing it even more, right? It's like saying, well, this 100 now is increased to plus infinity. It can be anything, right? The number of used resources. It's not limited to 100 or 120. It's even limited to, not limited at all, right? So the maximum limit is infinity, right? So we could say that both cases that we're asking here about are relaxations, right? So now the optimal solution will still be optimal, and the optimal objective function value will not change, right? It's still the same. Whatever it was, I don't actually know it, right? I don't have all the information about the model, right? But I know this optimal solution 1020 will still be optimal, and whatever the objective function value of it was, it will still be the same. And actually, I don't even care if it was maximization or minimization, it will not change, right? Here is another question. An optimal solution, again, is 1020, and the model contains a different constraint now, 2x1 plus x2 greater than or equal 40. What if we decrease the right-hand side of this constraint, or what if we remove this constraint from the model, the original model that we were solving here, right? Again, we don't have full information about it. But this time, if we calculate the left-hand side value, right, if you take 2x1 star, right, plugging in the value of the optimal solution, x2 star, right? So if we calculate this and we put 2 times 10 plus 20, right, it will be 40. You'll see that the slack, right, the slack, which is absolute value right-hand side minus left-hand side, equals, right, what is it? 40. Right-hand side is 40, and the left-hand side we just calculated is also 40, so it will be 0, right? So the slack is 0, so it is possible that this was a binding constraint. It is possible that this was a binding constraint. Right? Why am I saying, not saying for sure? You see, because if the slack is 0, we would have to check the shadow price, and if the shadow price for this constraint is not 0, we would be sure this is a binding constraint. But there are rare cases where the shadow price could also be 0, and in that case it could be just a coincidence that because of other constraints, this constraint is also satisfied with equality, but in fact it is not binding in the model. So, right? So, but it is possible that it is binding. I don't have access to the shadow price to be sure, right? But assuming it is binding, right, I would know that, right, this case applies, right? I'm relaxing a binding constraint again, and again, both cases, decreasing the right-hand side here, this is a greater or equal constraint. So if I decrease this 40 by 10, I make it 30, I make the requirement easier, right? So I allow more feasible solutions. Or if I remove this constraint, this is as if I'm saying this becomes minus infinity, right? So really there is no restriction, minimum value of this, right? Both cases are relaxations of the model. So what we say, right, the optimal objective function value might improve or stay the same. So the optimal, right, I could say the optimal objective function value will improve or stay the same, and the optimal solution might change, right? Why might it change? If if the optimal objective function value improves, then clearly it improves because the solution changes. So last example of relaxation, what if, right, we have again an optimal solution 1020, and what if we have a constraint that is an equality, and what if we remove this constraint, right? So again, we check that this constraint, right, if we plug in x1, x2, right, on the left-hand side, right, x1 plus x2, plugging in the optimal values, x2 star equals, right, this is equal 10 plus 20 equals 30. And of course, this is equal to the right-hand side. So that shouldn't be a surprise, obviously, because, right, this constraint has to be binding. An equality constraint has to be binding, the only exception being if it is redundant. If there are other constraints that actually imply this, then it doesn't have to be binding. It could be removed from the model and it would still be satisfied. But otherwise, these kind of constraints are always binding, right? So removing this constraint, this case, we should be careful and apply this case, right? So equality constraint, right? This is no surprise, right? So I can actually remove this. This is just a formal check if, let's say, someone who put this question did not make a mistake, right? If this was not equal, this would be an infeasible solution and wouldn't be optimal, right? So this obviously has to be satisfied. So what I need to say is that equality constraint is always binding except when redundant. So optimal solution might, so this case applies, right? The optimal, right? And removing it is a relaxation. So the optimal solution will improve or stay the same, and the optimal objective function value will improve or stay the same, and the optimal solution might change, right? And I want to emphasize here that if we were, for example, to add a question here, what if we increase this 30 or what if we decrease this 30? We couldn't actually say if this is a relaxation or a restriction. Would be neither, right? Because notice that there are certain points that satisfy this equality, right? The sum equals 30, and if I change this to 25, the old feasible solutions, all of them become infeasible, and there is a new set of feasible solutions, those that satisfy this equality of exactly 25. So basically the feasible region changes, and it's neither relaxation nor restriction. Okay, so let us now talk about the reverse of what we, right, the reverse of relaxation, which is the restriction of a linear programming model. Well, a restriction, obviously, if relaxation was expanding the feasible region, a restriction will be like contracting, reducing the size of the feasible region by making constraints more restrictive, right? So for example, if I add a new constraint, I might be restricting a model. If I decrease the right-hand side, like decrease available resource, or I increase minimum requirements, or I increase the right-hand side of greater than or equal constraint, I will be creating a restriction. When we restrict a model, the opposite might happen to, right, the relaxation. So the optimal objective function will become worse, or it will stay the same. But again, we can figure out a lot without having even sensitivity analysis, as long as we know the optimal solution, because we can look if the old optimal solution satisfies this new restriction. And if it does, it will remain the optimal solution. And if it doesn't, it will change. And right, so we can also add here, when we restrict the model, the optimal objective function, right, will worsen, but it will worsen whenever the old optimal solution becomes infeasible, right? Then we will have to change the optimal solution. In that case, the optimal objective function value might become worse. So let's consider some examples. So suppose, again, we have a model that I don't have all the details for, but I know that the optimal solution of the model is 10, 20, and the model contains constraint x1 plus 3, x2 less than or equal 100. So what happens if we decrease the right-hand side of this constraint by 20, right? So, right, this means the constraint will be 100, x1 plus 3, x2 less than or equal 80, right? So this constraint is going to be tighter. It is a restriction, right? It's the case where we decreased, this is the case, decrease the right-hand side, right? So let's check if, what do we need to check? Well, we need to check if the old optimal solution, this 1020, if it actually satisfies this constraint, right? So the question is, right? If we plug in the left-hand side the optimal solution, x1 star plus 3x2 star, right? If we plug it in and we get 10 plus 3 times 20, which is 70, right? And we check, is this still less than or equal to the right-hand side, which is 80, right? Right, and it is, right? So, if this optimal solution, the old optimal solution is still feasible, right? Right, and notice that this is a restriction, so we have not increased the size of the feasible region, we actually reduced it. So we don't have new feasible solutions that could be better than this the old optimal solution. We actually reduced the size of the feasible region. So if this was optimal for a larger set, and it will still be optimal for a smaller set, provided that it is still feasible, and we just showed the optimal solution is still feasible, so it will still be optimal, and the optimal objective function value will not change, right? So this is the case where, we checked, so notice what the procedure is. If you have a new constraint or a restricted constraint, just check if the old optimal solution is still feasible, if it still is feasible, and this is a restriction, right? So, and this is a restriction. So, the optimal solution is still optimal, right? The old feasible solution, feasible. The old optimal solution will still be optimal, and the optimal objective function value will not change. Here is another question for restriction, right? So suppose, again, we have a solution 1020, and the model contains constraint 2x1 plus x2 greater or equal 40. What if we increase the right-hand side of this constraint by 10? So, of course, the constraint becomes, right, 2x1 plus x2 greater than or equal 50, right? And now left-hand side at the optimal solution is, right, this 2, but 2, when we plug in the optimal solution, right, plug in the optimal solution, this becomes 2 times 10 plus 20 equals 40, right? And that, we would like this to be greater than or equal 50, which is the right-hand side, right? However, it is not, right? It's not greater than or equal to 50, which is the requirement here in the constraint, right? So this restriction makes the old optimal solution infeasible, right? So, right, the optimal solution will change, and the optimal objective function value will be worse or stay the same. So we should expect it to be worse. So let's say if this was profit maximization, we just cut off the most profitable solution, so that means we might get worse profit. However, there are cases where we had, right, they stay the same, the same, right? This last case, when it stays the same, this might happen in case where there were multiple optimal solutions to start with, right? So it could stay the same if this solution becomes infeasible, but if we had multiple optimal solutions, maybe there's another optimal solution of the original model that is still feasible for this new constraint, and we could choose it, and in that case, the optimal objective function value would actually not become worse, but it would still be the same, but the optimal solution certainly will change. Okay, one more one last question will be, what if optimal solution is still 1020, and what if we add a constraint, and this is question 3, add a constraint 7x1 minus 5x2 equals greater than or equal to 0, right? So this is a new constraint, so this is the case here, right? Adding a new constraint is a restriction, right? It may be that it cuts off some feasible solutions, and we actually don't know. We cannot find this easily because we would have to see the whole feasible region. Well, with two variables, we could actually plot it, but we don't have all the information. But what we can determine is for this constraint, if you plug in, we can evaluate the left-hand side of this constraint, right, at the optimal solution. So that will be 7 times 10 minus 5 times 20, right? So that's 70 minus 100, which is minus 30. Now we would like this, for this constraint to be satisfied, this value should be, right, greater than or equal to 0, but it is not greater than or equal to 0, right, which is required by the constraint. So if this restriction, right, is introduced, right, this is a restriction, the old optimal solution is no longer feasible, right? So again, we have the case where the old optimal solution is no longer feasible. So the optimal solution will change, and the optimal objective function value, right? The optimal objective function value will worsen or will stay the same, and the latter might happen if there were multiple optimal solutions in the original model, right? So then in that case, even if the optimal solution changes, which we know for sure it will change, right? We know for sure it will change. If there were multiple optimal solutions, it might be possible to select another of those multiple optimal solutions that actually still satisfies this constraint, right? So this is the last question about relaxations and restrictions. And notice that here we have applied several we were able to actually, in several examples, we were able to conclude what happens without actually using sensitivity information, just knowing the optimal solution and determining, for example, if the constraint that we're removing was binding or not. We could, in the relaxation, conclude if the solution will change or not. And in the restriction, all we need to do is, if you have the new restricted constraint, you plug in the old optimal solution and see if it is still feasible. If it is, it will remain optimal. And if it isn't feasible, then the optimal solution will change, and the objective value might worsen or stay the same.